What would you do in this situation? The Angels are tied 2-2 with the Diamondbacks in the bottom of the fourth inning, and Joe Adell is on third base with one out. Jorge Soler steps up to the plate and hits a sacrifice flyout to shallow right field.
A little bit here in this spot. Soler whips one toward the right field line. Adell goes to tag up. Carroll's on the run.
We see that Joe Adell has chosen to tag up from third and attempt scoring. Do you agree with this decision, or should he stay on base and see what happens in the next at-bat? This is a multifaceted question that can prove quite challenging even for the most experienced coaches to answer, but we can utilize the concept of expected value to inform our decision. Expected value is a powerful concept in statistics that is actually quite simple. To understand expected value, we must first understand the concepts of experiments and random variables. In statistics, an experiment is any situation with an unknown outcome. For example, an experiment could be tossing a coin, where we are unsure whether the outcome will be the coin landing on heads or tails. Random variables are often associated with experiments, like the number of runs batted in during a plate appearance, where anywhere between 0 and 4 are possible. This is quite a lot of uncertainty, and expected value comes into play perfectly to help us better navigate these tricky situations. Expected value is used with random variables in a literal sense, to note the expected value of said variable. Often, we think of expected value as the average value of a random variable if we perform an experiment numerous times. Generally, the expected value of a random variable can be calculated with the following formula. In this formula, we sum over all possible outcomes, the product of each individual outcome, and the value of the random variable for the respective outcome. Consider the following example. We want to find the expected value of tossing a fair six-sided dice. Since the dice is fair, we have an equal probability of obtaining each outcome. If we define the random variable x as the number of dots that show up when we toss said dice, the expected value can be computed as follows. The expected value of x is equal to the sum of the product of the probability of obtaining each dice face, 1 out of 6, multiplied by the number of dots on the dice face, 1 through 6. Simplifying this, we see that the expected value of x is 3.5. We expect that in the event of tossing the dice multiple times, the number of dots that show up will average out to 3.5 in the long run. In baseball, games are won by scoring more runs than the opponent. Therefore, our decisions will be influenced by our knowledge of the expected runs scored in various situations. With that in mind, here's a run expectancy matrix detailing the expected runs scored in various situations for this year's MLB season, accurate up to May 29, 2025, and sourced from Fangraphs. The darker green shaded boxes are situations where we expect more runs to be scored, and the lighter, almost white colored boxes are where we expect less runs to be scored. The columns represent the number of outs in a half inning, 0, 1, or 2, and the rows represent the runners on bases. As we intuitively would guess, the highest expected run scored comes from having the bases loaded and no outs, while the lowest expected run scored comes from having the bases empty and 2 outs. Let's think back to our original scenario. Joe Adell is on third with 1 out, and the ball is hit into the outfield and caught for the second out. There are 3 results. First, if Adell tags up and scores, we have 2 outs and nobody on, which is worth 0.1 runs. Second, if Adell tags up and is out, we score no runs and the inning is over. Finally, if Adell does not tag up, we have a runner on third with 2 outs, which is worth 0.32 runs. We can see these expected run values in the following bar graph. Let P be the probability that Joe Adell successfully tags up. Then we need to solve the following equation for the value of P. In the above equation, we calculate the probability of successfully tagging up, P, multiplied by the outcome, 1 run scored, then subtract the probability of the tag up failing and getting out at home, 1 minus P, multiplied by the outcome, 0 runs scored, since we would have 3 outs in total. We want this difference to be greater than 0.32, the expected run scored if Adell simply stays on third and we let the next batter of the inning step up to the plate. Simplifying this equation, we see that P must be greater than 0.32. With this in mind, we see that Joe Adell should tag up from third even if he has a less than 1 in 3 chance of succeeding, which is initially quite shocking. However, if we were to take a moment and think about the reasoning behind this, it begins to make much more sense. The next batter is much more likely to make an out, either by striking out, grounding out, or even flying out, than to get some form of base hit that will allow our runner on third to score. As such, it makes sense that Adell decides to attempt tagging up on this play.
Makes the catch. Here comes Adell. Carroll with a good arm. Throw to the plate. It is not in time. Adell is safe as the Angels take a 3-2 lead on a sac fly.
Despite it being a close play at home, Adell undoubtedly beats the throw and scores the go-ahead run for the Angels in the bottom of the fourth, a lead they would hold on to for the rest of the game. Overall, expected value is a wonderful tool that we can leverage to help inform our decision making in everyday life. You can keep an expected run matrix as an image on your phone, and let me know if that helps you make the right decision during the next game you watch.